Hi all, welcome back to another week of Math 400. Got some wave equation stuff to do this week, which is really a continuation of the first order equations that we have been looking at, which have wave-like behavior. We'll see the full story for what is the standard wave equation today, and do some analysis of it. Okay, let me share and let me reduce that so I can see the Slack channel in case you've got questions, and make some room here. Okay, so we're going to leave nonlinear equations. So we're going to go back to the easiest kind of equation, linear constant coefficient ones. Where we left off with linear constant coefficient equations was with scalar first order equations. Most of our discussion has been without boundary conditions. So we've been talking about what's called the Cauchy problem, where you're interested in the behavior of the problem for all x, and you give initial conditions for all x. Not all kinds of problems are well suited to a Cauchy problem, and we'll see that coming up. So just to remind you, what we did here is we wrote characteristics. These are curves that come from the initial data. So they start at x equals s and then move with speed a. And then we had this nice little trick where we look at how u changes on those curves. So that's u of x of t and t. And so when we do the chain rule, we get two parts. Get x dot du dx plus du dt. And that's a du dx plus du dt. And then we look back at the PDE. Right, and we see that that's equal to 0, so that tells you that u is constant on these characteristics. Dix, okay, sorry, I ran out of room there. And so u on the characteristic is the same thing that it was on the initial conditions, where the characteristic came from. And if we want to invert this, so we get u of x and t, then I have to look at the s value that is x minus at, and we get the explicit form of the solution is u0 of x minus at. So this is a wave moving with speed a. If a is positive, it's moving to the right, and if a is negative, it's moving to the left. Okay, so there's a quick reminder of how we started the discussion we've been having for the last few lectures on first order equations. If we wanted to talk about how this fit in with our kind of basic ideas about solving PDEs, you know, qualitatively or quantitatively. We've got two main ideas. One is series solutions, and the other one is sort of Green's functions. Remember, a Green's function is really an explicit map of data to the solution. And so this has the character of a Green's function. Because it's a pretty clear map of the initial data to the solution. The initial data is the only data we have in this Cauchy problem for this first order equation. And so if we were going to write it as it says typical Green's function, so the integral of the initial data, then we'd have to get into the game of generalized functions. It would be like a point mass that would describe this Green's function. So that's a Math 401 kind of story. So we'll leave that for Math 401 for those of you that are taking it. But certainly you can see if you had to say this kind of solution was a Green's function or a series solution, well, there's no series going on here. So it's a Green's function. And it has that character of explicit map of data to solution. Okay, so that's old news. Let's go on to something new. I think this is really a sort of an aside, and then we'll pick a particular example that's going to get us to the standard wave equation. But let's at least start with the vector case. And when we talk about vector first order equations, we can also talk about conservation laws and shocks and everything, but that's a bridge too far for Math 400. So we're going to stick with the linear constant coefficient ones. Right, okay, so I'm going to have a vector u of x and t with n components. Okay, you're all very quiet out there. Someone chat or say something so I know someone's out there.
Something. There, I said something.
Thank you, Matthew. Yeah, I'm mostly awake as well. I could have used another cup of coffee this morning. Okay, so I'm going to have my vector with n components. You've seen my vector notation before. It's just the underline, right? So I'm going to have the vector ut plus a matrix A. So this will be an n by n matrix times ux is equal to 0. And it will be the Cauchy problem. So defined for all x, I'm not worrying about boundary conditions. And I've got initial data for all x. And I'm gonna say for this to be a wave type problem, A has to have real eigenvalues. Okay, so one of the ways we can sort of say that A has real eigenvalues and has some, pretty nice properties. We've seen this before. Is let's pick the matrix A to be symmetric. So it's going to have real eigenvalues. And I can make the eigenvectors orthogonal. And I might as well normalize them to make some of the algebra a little bit easier coming up. So I've got A times Vj is lambda j Vj, and the length of these vectors is 1. So there's no normalizing that has to happen. Now I'm going to write out what happens, and we've looked at these kind of Eigen decompositions before. I'm going to do it a little bit quickly, but let me at least give you the flavor. This vector u, right, at every point of x and t, you can write in terms of its eigen coordinates, and the coefficients of those coordinates are going to have equations that look exactly like our first order equation where A is lambda j. So I'm going to get a bunch of different components of the solution. So different Eigen components are going to move in this simple constant coefficient linear way with speed lambda j. Okay, and let me show you the algebra that leads to that. So we can write, now this is nothing to do with partial differential equations yet. I can just say, hey, I've got a vector solution at every x and t. I'm going to write it in terms of these Eigen coordinates. And so the coefficients, of course, because the vector depends on x and t, the coefficients will depend on x and t. Vj, though, A is a constant matrix. We can do this whole game with A depending on t, but that's more complicated. So this is just going to be constant in time. In the lingo, this is an autonomous problem. Okay, so Vj is not depending on time, but the coefficients could. And I can work out those coefficients at time 0. That's easy, right? I just take the initial data and I take the jth component, right? And because these vectors are orthogonal, right, it's easy to figure out the Eigen coordinate. You just take the dot product with the eigenvector, and there would normally be a normalizing term that would come here, the 2 in the sine series kind of thing, except that I've picked them to be normalized. Okay, so now if you take this here and you put it in the PDE, right? Now you can see that everything separates out into Eigen coordinates. Oh, I got a couple of things. I missed this. Everyone is saying hi in chat. Okay, thank you. To what extent can you use eigenfunction decomposition to solve ODEs? Like, where does it break down and you have to use another method? Otherwise, why don't we just always break U, the non-vector case, into superposition of its eigenfunctions? That's an excellent question. In fact, one of the things that you started with when you were looking at vector ODEs was exactly break it up and use superposition. Okay, where that breaks down is if A depends on time, okay? And then at every time, you might have an eigenvector, a decomposition, but because it changes in time, then these vectors will change in time. And once you take this thing and put it in here, then you're going to get an extra term of the change of the eigenvectors with time. And then you can't do this nice game where everything separates into scalar case. It's like it's all coupled. Now you can get some insight into how it behaves, but you can't actually see the whole story in that case. Is that a sufficient answer? And of course, once you've opened up the door to cases that aren't constant in time, then you can talk about nonlinear problems, right? Okay, and then this whole game is changed as well. If A depends on U, well, then in X and T, then the whole thing could be different. Okay, but let's not take away the power of this thing for constant coefficient problems. It's good, and for those other problems, even though it's not exact, it can still give you some insight into what's going on. Okay, so I'm going to take this, I'm going to put it in here. The time derivative doesn't change the directions. And when I multiply by A, because they're eigen vectors, that also doesn't change the direction. And so I get a bunch of stuff which separates nicely into the eigen components, and I get the following. So I'm going to get Cj. Now in the notes, I thought the Cj, this is this coefficient of the solution in its eigen vector decomposition. So in the notes, I write the time derivative of this as Cj comma t. Well, okay, maybe it would be a little bit less confusing if I put the time derivative like this, right? And then over here, I've got the A times the vector. And if I look at the eigen component, that's going to be lambda j. So this is just our first problem today. For all j. So I can write Cj of x and t is just Cj at x minus lambda j times t at time 0. And that's the initial data inner product with the vector. Okay, and let me draw you a picture of how that looks in the xt plane. Here I've got a point xt. I want to know the solution here, right? Well, it's a vector, so I need to know all of its components. Well, I'm not going to work it out like one standard component at a time. I'm going to work it out in terms of one eigen component at a time. And let's suppose I've got lambda 1 is 0, lambda 2 is, what did I pick? 1. I just picked some stuff that kind of made a nice picture, at least what I thought was a nice picture. So I've got something that's not moving at any speed at all, right? So it's going to go straight back down to the initial conditions. This is going to give me one of the components of my solution, right? And that component is going to be the eigenvector 1 component. So I work out what that component is here, right? And the component up here is the same, okay? Now, unlike in the scalar case, though, this is not the whole story, right? Because there's other components I have to work out, and they're not all following the same line. They're following different lines. Because if I look at lambda 2 is equal to 1, right, I have to start here. I have to go backwards with speed 1. And here is where I'm going to get the V2 component of the solution. And of course, I get that by looking at the V2 component of the initial conditions. Oh, yeah. Let me get this right in my notes. Right, and then this one, this last one, right, I've got basically 2 pieces of information about the solution at x and t. I need, it's a 3-component problem. I need another one. I'm going to get the third eigen component information on this line. And the initial data that I'll need will be u0 at x plus t over 2. and I'll need the V3 component of it, right? So it's a Green's function, right? If you walk this all through, right? It's saying, how do I get this solution here in terms of the initial data? Well, it's a sum of three things, right? I take the V2 component of the initial data here. I add the V1 component of the initial data here, and the V3 component of the initial data here. And I add those up, and I get the solution at that point. And if you can think about it in your head, okay, maybe this is a bridge too far. But the complementary problem is if I give you some forcing, but no initial conditions, right? How will the solution look like at this point? Well, I'm going to get exactly this kind of thing, but with an F on the right-hand side, right? And not just any F, but the jth component of F, and it'll be along the characteristic. And so in that case, what the solution will look like is, well, I start at 0 here, right? Because all the components are 0, right? And then I integrate the, what's this one? This is the 2. I integrate the F function. It's a vector F. Did I put a vector on it? No, I didn't. It's vector F. I take the dot product with V2, that gives me the second Eigen component, and I integrate that along this line. Integrate the dot product with V1 along this line, and I integrate the dot product with V3 along this line to get the solution. So you can see that directly from this construction, and you could also see it from the from DuHamel's principle, which I know is a little bit mysterious, and we're going to revisit that today in a more general setting, which will hopefully help. We'll see what happens. Okay, so vector case. So I'm going to pick a particular example of a symmetric A that's going to lead us to the standard wave equation, which many of you have seen before. Many, maybe all. So let's consider now the n equals 2, A is equal to 0, 1, 1, 0 case. This is going to lead us to the standard wave equation. But because now we have an understanding of these first order equations, and now we have an understanding of these vector first order equations, maybe this is a good place to start to see what we're going to expect from the wave equation that comes out of this. So I'm going to look at this problem. Cauchy problem. Right, I can do the eigen analysis of this. This is something I can do even in my head. I'm going to have eigenvalues 1 and -1. So I'm going to have this is a problem that's going to give me waves traveling to the right and to the left with speed 1. The eigenvectors are pretty simple. I haven't normalized them because there would be 1 over the square root of 2 stuff going on. I didn't want to write that all out. Okay, so I got eigenvalues and eigenvectors. And so I know I'm going to have a picture like this, where the solution is going to be determined along lines going from +1 and -1. And we're going to see that in the solutions that we're going to find for this problem in a different form. So let me show you that form. So now I'm going to think of this vector u as having its two components, u and v, scalar u and scalar v. And if I do that, I can write out the two equations that come. That's ut plus vx is equal to 0. that's vt plus ux is equal to 0. And I can take the derivative with respect to t of that, as long as solutions are smooth enough. And I get utt plus vxt is 0. I can take the x derivative of this one, as long as solutions are smooth enough, and I get vxt plus uxx is equal to 0. And I'm going to use this. I mean, this A is pretty simple with the zeros. You can see that something could happen, right? And so what I'm going to do is I'm going to eliminate V, because I see the same term that's showing up in both terms. And I'm going to get utt is uxx. So this is the standard wave equation. And you can see that it can be derived as an equivalent to a simple vector system of first order equations. So that's one way you can derive the wave equation. So you can derive the wave equation from a kind of vector system. This is the typical way it's done for kind of pressure waves, like sound waves in air. There's a pressure, there's a, what is the other variable? Oh, I've forgotten. Velocity, density, maybe. Anyway, there's a system you can do. Now, if you want an actual derivation of the wave equation, you can look back to lecture number 3 notes. In the actual lecture, I just derived the equation for this weighted stretched spring. But in the notes that are posted, it goes on to talk about the problem where there's no gravity, so the stretched string just is horizontal, but you have movement in perturbations. So you give it a little whack, and you watch the vertical displacements move up and down. So there's a wave equation that comes from that. So you can see how that goes. Now we're going to spend the next little while talking about this equation, one of the big 3 of second order equations. One of the next things we'll do is talk about the sort of classification of those problems. We've got Laplace problem, we've got the heat equation, and we've got the wave equation are the 3, and they're a generic 3 in terms of second order equations in 2 variables. And like I said, we'll see that. That's a thing you have to do in Math 400, is that classification. So it's a second order problem. So if I talk about the Cauchy problem, so that's the problem for u for all of x, then you have to give initial data for the value and its derivative. So I'm going to give u of x and 0 will be u0 of x, and ut at 0 is u1 of x. And that's not surprising, right, that you need these 2 data. If you think back to ordinary differential equations, if you have a second order problem, initial value problem in time, then you need to give 2 initial conditions. And it's also something you can see from this vector case. It's really a vector problem, and so you have to give 2 components of something at time 0. Now, if you, and you'll see something that's a little bit different coming up. If you want to understand why they're different, it's that the initial data for this problem is really going to be, well, u0, right? That'll be one thing, but the initial data for the v is really going to be an integral of u1, and you'll see that as we come up in the form of the solution. Okay, well, whatever wave equation problem you want to solve, unforced, right? I've got no F, right? Whatever unforced wave equation problem you want to solve, there's a general solution. Well, that's pretty good, isn't it, right? So I'm going to say there is a general solution to the wave equation. No matter what other things that you add, unforced, it's got to be unforced. Whatever initial conditions you give, if there's boundaries, whatever boundary conditions you give, the general solution of the wave equation is this form. It's a function of x minus t and a function of x plus t, right? Well, okay, there's two unknown functions in the general solution, but they're functions of one variable, not of two variables. So you've made a big win with this formula. This is called D'Alembert's formula. And if you're wondering how you can derive it, there's two ways to derive it. One is from the vector form, right? We already know from here that the solution at this x and t has to come from the characteristics, right? And so the characteristics are going back with along these lines, right? Okay, so there's one way to do it, and those lines have to hit either an initial condition or a boundary at some point, and so that's gonna tell you that this is true. The other is to do a coordinate transformation. So I'm going to have two coordinates, x plus t, and eta is x minus t. And if you look at, you do all of the change of variables, right? And you'll see that the wave equation ends up being u c eta is equal to 0, right? Which means if I take the partial derivative with x plus t and then the partial derivative with respect to x minus t, like I get nothing, right? And that leads directly to this form. You got a g of c and an f of eta, or actually, oh yeah, that is right. I was going to say or the other way around, and that's the only solution you can have for this. Well, the general solution you can have for that. You can also talk about the wave equation with speed c, and you get a utt. Let's see if I can put the c in the right place. C squared uxx, or it's often written this way. Right, and this has general solution. A wave moving to the right with speed c and a wave moving to the left with speed c. Okay, but now we know about scaling. We could just scale time to make c equals 1. So let's just stick with the c equal 1 problem. Now that we're in this Math 400 class, we know that drill. Okay, well, we've got a general solution. We've got a Cauchy problem. Let's solve the Cauchy problem with the help of the general solution. So we'll match the f and the g to the u0 and the u1. And we're going to use the same trick that we've done before. We're going to divide this up into two pieces, right? We can solve with u0 given and u1 is identically 0, and then solve the other problem. So I'm going to have two problems that I'll use. Okay, so let's solve Cauchy problem with u0 given and u1 identically 0. Right, and so I know I can start with this general form. Okay, why did I put g first, I wonder? F of x minus t plus g of x plus t. And I can apply the boundary conditions. So I can take that form and, oh, why is that y? Should be t. I can look at that general solution at time 0. That gives me f of x plus g of x. That's equal to u0 of x. That looks pretty good. I can take the time derivative and evaluate it at 0. Well, if I take this time derivative, I get a minus f, right? And then when I evaluate it at 0, oh, minus f prime, sorry. And then I get a plus g prime of x. This is equal to 0, right? And I can integrate this and say minus f of x plus g of x is some constant, right? It's an arbitrary constant of integration. Okay, and I can look at this and I can look at this and notice that this is a linear, an easy linear algebra problem for f and g at every x, right? And in the prepared notes that were posted, it's saying add me, subtract me, right? This is what this is yelling at us to do, right? So it's a linear system. Normally you have to put it in a matrix and do the solve, but this one is an easy substitution. If I add these two things together, right, the f's cancel out, and I get g of x is 1/2 of u0 of x plus c. And if I subtract them, I get f of x is 1/2 u0 of x minus c. Okay, and I notice in the notes, instead of G, I've used B. So I had F and B. Oh, that was supposed to be tricky. F for forward, B for backward. But okay, I messed that up. So now I'm going to put it back together. Now I've got U of X and T. It's the F of X minus T. So it's I'm going to have a 1/2 u0 of x minus t. Notice when I add f and g, the c cancels out, right? So this thing, which was an arbitrary constant, I didn't know what to do with. Well, okay, yeah, it was just an artificial intermediate thing that won't affect the final solution. Right. Okay, and let me come back to a comment I want to make. But we can describe this in words. So in words, what happens with my initial data? This profile breaks up into two pieces. And one moves to the right. With speed 1. And one to the left. With speed 1. you've probably seen this D'Alembert solution before, but I am happy to show it to you again. And there's a nice little picture we can draw. Right, I'm going to give X. I'm going to have the, here's my initial conditions will be this kind of bump. And then if I look at some later time, I'm going to get that half of that bump. Okay, it's supposed to be half as high. I didn't do a good job. So imagine this is half as high as this. And then I'm going to have another one half as high, right? And then this bump is moving this way, and this bump is moving this way. So this is U of X and T for some later time. And if I wait even longer, those two bumps will be separate, and it'll be this shape, but half as high, right? One moving to the right, one moving to the left. Okay, let me warm you up for some abstraction, which is going to come later on. Okay, let's look at this formula a little bit more carefully. So this is the formula for the solution to the Cauchy problem, where I give initial data for U as U0, and I give 0 initial data U1 for the time derivative of U at time 0. So this is really a map from U0 to U of X and T. So again, we can think of it as a Green's function, as long as you're comfortable with the idea of Dirac delta functions. But that's not necessary for Math 400. It's a map, right? And I want to think of it in a little bit of an abstract way. I want to think of it as a map that takes all of U0 to all of U of X at time t, right? So U0 in this thing now, I'm not putting the bracket X because I'm thinking of it as the whole function, right? I take the whole function and I do some stuff and I get the whole function at U of T, right? Of course, it's a function of X. And so if I get U at T, I mean, I'm getting all of the function U, right? And I'm just going to have some notation for that. It's a map. It's a linear map. I could describe it by what's called an operator, which is basically just an infinite dimensional matrix, right? It's, you know, that's not important. There's a process by which I take U0, the whole function, and I get U at T, the whole function, and I'm going to call that process phi 0. So this is going to be the phi 0 that's going to show up later on in the lecture when we talk about DuHamel's principle. Okay, and because those underlines look like maybe I was talking about a vector, let me get rid of them. So this is just going to be notation. Right, for if I've got a second order problem in time and I figure out the map of the initial conditions to the solution at a later time, where I've got initial conditions for U and 0 initial conditions for its time derivative, that's what I'm going to call it. And of course, I'm going to have phi 1, which is going to be the same kind of map for when I have 0 values, but given time derivative initial conditions. Okay, so we're going to go ahead and work out what phi 1 is. That's the complementary problem where I'm going to give U0 is 0 and U1 will be given. I'll do that next. But we haven't had a poll in a while. I had intended to do one every lecture, and of course, well, you know, things don't always, you know, go the way you plan them because you forget, basically. So I've got a poll for you. Let me see if I can find it. It's anonymous. Okay, we got a minute. It's fast. I can share. It's kind of all over the board, except poor Green's functions. Poor Green's functions have no love. I love your Green's functions. It's okay. I'm going to, if I remember, I'm going to do the same list of topics next time, but I'm going to ask which of those topics could use the most note revision. So which ones could benefit from you know, updated notes on them. So you can think about that for next lecture. There's only a few people, you know, now attending live lectures, but that just means your voice counts for more than it did before. So I'm happy to put some work into the notes that I've posted so far and update the ones that you find the least informative. So that's what the question will be for these topics next time. Okay, so we've solved for one of the Cauchy problems with D'Alembert's solution. Let's solve for the other one. So now let's solve U0 identically equal to 0 and U1 given. That's the du dt at time 0. Right, and then if we've got a problem where they're both not 0, we can just take the two solutions and add them up because it's linear, right? Linear is nice that way. So I need to make x at 0 equal to 0. I've got f and g instead of f and b like in the notes, but if you see a b, it's really a g, right? Okay, now I have to take the time derivative of f of x minus t plus g at x plus t. I have to take the time derivative and set it equal to 0. Well, that's going to be the same kind of story. F prime of x plus b prime at x is equal to u1 of x. Now I have to integrate to proceed. And that tells me that minus f of x plus b of x is equal to, now I'll call this capital U. This is an antiderivative of u1 of x. So I have to integrate the initial data, right? That's the thing I was trying to hint at you before about the difference with the vector case. That the initial data for the V is really like an integral of the U1. This is where this comes up. So it's going to be U1 that's going to affect the solution, capital U1. But we will want to write out our solution in terms of the data the way it's actually given, which is the little U1. And you'll see something a little bit different will come up. Okay. So anyway, I've got the same linear algebra to do with those two linear equations. The add me, subtract me is still shouting out. And what you're going to get is the arbitrary constant in this antiderivative falls out the same way the C fell out before. And I'm going to get U of X and T is equal to 1/2 U1 of X plus T minus U1 at X minus T, right? But this is the capital U, that's the antiderivative. And if you look at the difference of two antiderivatives, that's just the integral, right? So I'm going to have 1/2 the integral from X minus T to X plus T. Now I'm going to have little U1 of X dx. This is the data the way it's actually given, right? Yeah, so we can write this out in terms of a way that the solution depends on the initial conditions, right? We can also write it in terms of like a wave. And so there's some stuff, but it's not exactly U1, it's U1's integral, right? Which will break up into two pieces, but they're going to be pieces of opposite sign. One will move to the right, one will move to the left, but they'll have opposite signs. And again, just to kind of warn you about what's coming up, I've got this whole function U, right, at time t, coming from U1 at time 0, and I'm going to have notation for that. It's going to be U at time t. That's the whole function. Is going to be this phi1 of t times U1. Okay. Let's see. I always have more to get through in a day than I can actually get through in notes. We'll see how far we get. It's also my philosophy for when I have people over for dinner, make sure you have more food than they can possibly eat. I think that's just being a good host. Now let's look at UTT is UXX plus F of X and T. So now I'm going to have the forced problem, but with no initial conditions. Now, when we've had the forced problem before, we've found solutions and we've recognized that they always come from this DuHamel's principle thing, where it's always the integral of F considered as initial conditions, basically. So let's do an aside to figure out how we would use DuHamel's principle to solve this problem. Right, so let's derive DuHamel's principle. Because we kind of know DuHamel's principle, but only for first order equations. We got a second order equation now, second order in time. So there's a question about what we do there, right? We've got these initial conditions, but we got two types, right? So what should we use to describe the F? And so we're going to derive a DuHamel's principle for problems that are second order in time. That'll be a new game. And let's recursively do an aside. So before we do that, so the aside to the aside is let's derive DuHamel's principle. In a formal way for first order problems. We've seen it, a number of examples of it, but we've never actually seen the abstract formulation of it. Okay, so this is not the wave equation. We're in the red zone. We've recursed twice into an aside. And we're back looking at ut is some linear operator of u with some forcing. And no initial conditions. Right? You notice that I've written it in this kind of operator form, right? The example we could think of is the heat equation with boundary conditions. So then the L would be the second derivative of the function u, right? With respect to x, and include the boundary conditions. So, right, and then f would be f as a function of x and t. So at every time, there would be some function of x that was the forcing term to the heat equation. We've also looked at examples where u is a vector, right? And so then the L could be a matrix, and the f would then also be a vector at every time. Okay, so this is, I'm trying to make this as general as possible. Okay, and just like we had started to say here, right? I'm going to say that this solution has the form. Oh, not this one. Sorry, let me go back. We're going to use DuHamel's principle to find the solution of this one in terms of the solution of the initial value problem. So let's look at that. So now we're going to look first at the pure initial value problem. So that's ut is equal to Lu with no f, and u at time 0 is u0. And I'm going to write the solution in the form that I've tried to foreshadow with the discussion up above. I'm going to write this in the form u at time t is some solution process times the initial conditions. Now again, let's just think about this. Now I've got no subscript on this phi because it's a first order problem. I don't have initial data for u and ut. I've just got initial data for u, so I know what initial value problem I'm looking at here. So let's just look at some examples of this process. So if we were looking at the problem that we started with in the lecture, I would get the solution at time t, right? At every x, what I would do is I would take the solution at x minus at, right? The initial data there, the u0 at that point, that's what the solution u of x would be. And that whole process, working out what u of x is at every point, would be in this, encoded in this capital phi thing. If I was solving a heat equation problem with 0 boundary conditions and constant coefficients, then the solution process at time t would be, I take the sine series of the initial data, right? And then I multiply by the e to the minus n squared pi squared t, each of the coefficients, right? Sum them up, that gives me the solution at time t, right? So this is a formal way of writing the solution process for whatever problem I happen to have, right? So now I can go back to the forced problem. And we've seen a number of examples where this works. The problem 1 is formally solved. By formally, I mean it's an expression which you have to make sure makes sense for the problem that you have by DuHamel's principle. In this case, is I get the solution to the problem with forcing but no initial conditions by integrating the forcing over all the previous times, pretending that it's initial conditions at that time. Right, we've seen a bunch of examples of it, but this is the formal statement of DuHamel's principle for first order equations in time. Well, okay. Let's go back and see what properties this has to have, right? What are the properties of phi? Well, I happen to know that if I'm going to have this satisfy the initial conditions, then phi at 0 has to be the identity, right? It'd be nice just to say write 1, right? Except, right, it's a function going to a function, so it's really a map. It's the identity map, right? When you look at phi at time 0 times u0, that should be the solution at time 0. So that means you've got to have the identity. The other thing it's got to do is solve the problem, right? And so I know that if I then put it into the differential equation, here is a very formal thing. If I take the time derivative of this operator, this is why it's formal, times any initial conditions, right? That's the ut. Then that has to be equal to L times phi of t times u0. And this is any time, any u0. That's what it means to be that solution operator. Okay, so let me check. Right? If this really works, then it has to, the u that comes out has to be 0 at time 0 and solve the equation with the forcing up here. That's number 1. So first of all, I can look and go at 0. I'm integrating from 0 to 0, I get 0. Okay, so that's good. I got that. Now the ut now has to be equal to L times u plus f. So let's take the time derivative of this thing. Well, it's got 2 pieces, right? It's got the piece when I take the derivative with the upper argument. And when I take it at the upper argument, s is equal to t. So I've got phi of 0 times f of t. Right, and I know that this is the identity. So this whole thing is going to be the f of t. That's pretty promising, right? Because I needed this f of t to show that that's actually a solution. And then I'm going to have the derivative of the stuff inside. So that's phi prime of t minus s f of s ds, right? But I know that if I take phi prime times u0 at any t, right, and for any right-hand side, it's just an L, right? And so now I can take the L outside. Remember, this is all formal, right? Okay. I've got the integral from 0 to 1. I've got the phi of t minus s f of s ds, right? And that was just the thing I said was u. So now I've got ut is f of t plus L times u. So this thing I've written down formally, this is the formal statement of DuHamel's principle in the most abstract way you can write it, but it's got the same spirit, right? Which is this idea that if you can solve the initial value problem, then you can solve the forcing problem, and the forcing just appears as integrated effect of initial conditions. Okay, so now let's go up on a side. We want to figure out DuHamel's principle for the second order in time problem. Right, so I've got UTT is L times U plus F of T. This is what we want to solve. We want to solve it with 0 initial conditions. Okay, and the question, which I know you're burning with curiosity for, is, well, can we do the same kind of game? And which one of the initial value problems do we use in DuHamel's principle? And it turns out to be the second one. So we're going to want phi 1. This is the one that solves the u0 equals 0 at the u1 given problem. Okay, so what do I mean by that? I mean, phi 1 of 0 is 0. Phi 1 derivative at 0 is the identity. And phi 1 of t times u1 solves UTT is LU no, right, homogeneous, with U at time 0 equals 0, U time derivative at time 0 is equal to U1. So I built in the boundary conditions already in my discussion, but I also need that phi 1 double prime times U1 is L times phi 1 U1. This is any time and any U1. Okay, so what is the formula for DuHamel's principle then? Well, it's basically just this one for the U1, right? So now I'm going to have U equals the integral from 0 to t. This is the initial value problem I have to use. This solves this one up here, the forcing term problem. So this is the statement, generic statement of DuHamel's principle. For second order problems. In time. Now this is pretty abstract, and there's the abstract argument that comes up to show that this works, similar to the one I just reminded you of for the first order case. And then we use the abstract DuHamel's principle to solve the force problem for the wave equation. And then because like maybe you just don't believe all of this formal stuff, then I show you that the formula that we come up with really works, right? You can take UTT and subtract UXX and actually get the f of x and t that you're supposed to get. Now, all of that's longer than the 1 minute I have left in the lecture. And because there's a little bit of kind of theoretical stuff to get your head wrapped around, maybe it's useful to be able to give you a little bit of time to look over the notes before we pick up next time. So I'm gonna end here. I will stop recording